Let's discuss a few specific nucleophilic additions to aldehydes in ketones. First one I want to discuss are oxygen nucleophiles. And these typically include water and alcohols. So if we look at a generic ketone, we can react that with water to produce what's called the hydrate, where you see that we've removed the CO double bond and we've ended up with two CO single bonds. And if we look at the components of water, we've added HOH to this carbonyl, and the original oxygen might be considered to be this one. And so we've added water to that carbonyl and we've made what's called a hydrate. We can do the same thing with an aldehyde. We add water, we end up with a hydrate. In this case, though, the hydrate has an H attached to that carbon of interest instead of two carbon groups. And if you remember our discussion on the reactivity of ketones and aldehydes, aldehydes are more reactive. And ketones are more stable. And it turns out that this reaction, at least, is in equilibrium, which means we have some reactant and some product present at equilibrium. And the percentages will depend on the reactivity or the stability of that reactant. And it turns out I'm going to increase this arrow to the left, implying there's more ketone present at equilibrium, and I'm going to erase some of this arrow that's pointing to the right. So the ketone is favored in this case. And in this case with the aldehyde, I'm going to increase the length of the arrow leading to the right to products, and I'm going to erase some of that arrow leading back to the aldehyde. Because the aldehyde is more reactive, it actually reacts quickly with water to make this hydrate. And so in this case, the hydrate is favored. We can also react ketones and aldehydes with alcohols. And they have pretty similar characteristics to the reaction with water. In this case, though, we need two alcohols because we need two H's. And we needed one water because we had two H's in the water already. And we'll form here a very similar structure where we have two single bonds to O. But in this case, instead of hydrogens, we have the two R groups, in this case the two carbon chain off of the alcohol, and this is called an acetal. Sometimes you might see it called a ketal, because in this case it came from a ketone, but generally most chemists will use this term to denote the addition of alcohols to both aldehydes and ketones. And we also made water, so let's balance our equation here. We use those two H's to make the H in water. One of the extra O's was the O in water, and then the other O, we'll put a dot there and a dot here. There are the two O's. And so that's the addition of an oxygen nucleophile in the form of an alcohol to an aldehyde or a ketone. And certainly if we start with the aldehyde, there's an H, we'd have an H off of this acetal. Hydrogen nucleophiles are also a common nucleophile to add to aldehydes and ketones. So let's look at, again, our favorite ketone, acetone. We'll react it with what's called sodium borohydride, NaBH4. And this has, you can think of this as almost a source of H-, meaning H with a lone pair. And that H can add as a nucleophile to the carbonyl carbon. And first step, second step might be mild acid workup. So there is the H that we've added as a nucleophile we've turned the O into a CO single bond, and the second step then adds that final H. And I'll put a box around this one so we can sort of keep track of where these hydrogens are coming from. And so this is reduction of carbonyls. And of course we can do the same thing with an aldehyde. And I'll use the same exact reagent, so I'll just put a ditto mark there. My new H that was added as a nucleophile, and my new OH, where this H should be my H in the box. We could also use lithium aluminum hydride. It's much more powerful. It does the same thing generally with aldehydes and ketones. So we end up with the same product. But this is more reactive than sodium borohydride. My organic TA like to call it the atomic bomb of reducing agents. And of course, in biochemistry, we don't have any sodium borohydride or lithium aluminum hydride present in the body, but we do have NADH, and that is essentially nature's reducing agent, and we can denote reducing agent with H in brackets, and so I'll put that up here so we're sort of reminded that that could represent sodium borohydride, it could represent NADH. NADH is nature's hydride source. And so we can obtain this extra hydrogen from NADH, and then this one is provided by some other proton source in the body. But this hydrogen came from NADH and again attacked our carbonyl as a nucleophile with this arrow push like we saw in some previous series of videos. So let's look a little closer at the mechanism of ketone reduction. We already looked at the ketone reacting with sodium borohydride to produce this alcohol, and this is a secondary alcohol that's produced from ketones. Aldehydes would produce a primary alcohol, and if we look at sodium borohydride in a little bit more of an expanded view, we see that the boron has 4 bonds to H, and because boron typically has 3 valence electrons, this gives boron a minus charge, and then that's why we need the sodium as the counterion, the cation in this case. And of course, we've already discussed how the boron or the borohydride acts as though it has an H minus that it can donate to the ketone. And so we can draw the H minus acting as a nucleophile and attacking the ketone just like any other nucleophile we've seen thus far. And we push electrons onto the O minus, or forming an O minus. And so that gives us this intermediate, where I've added this H from, let's say it's this guy here. He looks like that. But really the electrons are coming from this BH bond. And then the second step is very simple. Really all we have to do is protonate this O minus with the H3O plus, and you'll notice that is in here as the second step. And so first we reduce to form this alkoxide. Second thing we do is add H3O plus, a mild acid, just to protonate this O minus, and that gets us to our finished product. So it's a simple 2-step mechanism, a couple of arrows, and we see it takes after the normal nucleophilic addition to carbonyls, where the H minus in this case is the nucleophile instead of the O that we saw previously. So that's the mechanism for ketone reduction, and of course we can change one of these groups here to an H, and we have the mechanism of aldehyde reduction. So it's really not any different. It's just that there's an H on one side of the carbonyl. So while we're on the subject of nucleophilic addition to carbonyls, I thought it would be instructive to talk about C nucleophiles. So carbon nucleophiles. And really the most common one is this species right here, where we have a carbon chain attached to a magnesium bromide, and that's called a Grignard. named after a French chemist who studied this reaction. And really, what we have, when we look closely at this species, is essentially it's a carbon with 2 electrons in addition to the 2 hydrogens, plus this magnesium bromide species that is overall plus charge. And so you can kind of look at this bond as being sort of an ionic bond. We draw it as a covalent bond between carbon and magnesium, but really it is a highly polarized covalent bond where the carbon adopts a strong negative charge. And so now we can use this carbon as a nucleophile to add to the carbonyl. And so the mechanism here is the same as we've seen before, nucleophile attacking the carbonyl, creating the alkoxide. Gives us this species here where we have the O-, just like before. And now we have our new 2-carbon group attached to that carbon. So here, if I put in this methyl group, it might be a little more clear. That's a 2-carbon group. Here's my 2-carbon group. And in the second step in any Grignard, just like the second step in a reduction, is addition of mild acid. And then we can take this minus, attack the H+, and we end up with an alcohol now that has, instead of the 2 original carbon groups that we had on our ketone, they're there, but we also have this additional carbon group, and that came, of course, from the Grignard reagent. And so the proper way to report this is the first step is addition of Grignard, second step is addition of acid, and we turn our carbonyl into an alcohol with an extra R group on it.